The night sky is a vast, shifting tapestry of light, a canvas that has captured the human imagination since our ancestors first looked upward from the savannas. We watch the stars wheel overhead, marking the passage of seasons. We track the wandering planets as they trace complex paths against the background of the cosmos. But amidst this celestial dance, there is one object that dominates our view, a glowing silver companion that feels intimately close and yet profoundly mysterious. The moon. For as long as humanity has existed, the moon has been our primary lantern in the dark, a silent sentinel watching over the sleeping earth. Whether it hangs as a slender crescent in the twilight or dominates the midnight sky as a full, luminous orb, it possesses a quality that is both comforting and strange. It is the only celestial object whose surface features we can see with the naked eye. We trace the dark, basaltic plains of the ancient Maria, the seas of frozen lava that form the shapes we have come to know so well. We see the man in the moon, the rabbit, the toad, or the woman weaving, depending on which culture stories we grew up hearing. But there is something peculiar about these shapes. They never change, they never move. If you were to go outside tonight and look at the full moon, and then wait a week or a month or a decade or even 1,000 years, you would see the exact same face looking back at you. The sea of tranquility is always in the same position. The bright ray system of the Tycho crater is always near the bottom. The dark, circular basin of the Mare Crisium always sits near the edge. It is as if the moon is frozen, locked in a permanent stare, refusing to turn its gaze away from our planet. This unmoving appearance gives rise to one of the most common and understandable misconceptions in all of astronomy: the belief that the moon does not spin. It is an intuitive conclusion to make. When we watch a spinning top, we see all sides of it. When we observe the Earth from space, we see the continents drift by as the planet rotates, Africa giving way to the Atlantic, followed by the Americas and the vast Pacific. Rotation, in our minds, implies a revealing of all sides, a continuous turning that exposes every longitude to a fixed observer. Since the moon does not reveal its far side to us, it feels static, like a stone suspended on a string, merely being dragged around the Earth without any rotation of its own. However, the reality is far more elegant and geometrically fascinating. The moon is spinning. It is rotating on its axis with a consistency and precision that rivals the finest clocks ever built by human hands. The reason we do not see it spin is not because it is stationary, but because its rotation is perfectly synchronized with its revolution around the Earth. It is performing a cosmic ballet so well choreographed that the motion creates the illusion of stillness. To understand this, we must first shift our perspective from the surface of the Earth to a vantage point high above the solar system, looking down at the Earth and the moon as they move together through the velvet darkness of space. Imagine for a moment that the moon truly did not spin. Imagine it was just a rigid object, sliding through its orbit like a car driving around a circular track, but with its front always pointing north, for example. If the moon did not rotate on its axis at all, as it moved to the opposite side of Earth, the face that was previously looking at us would now be looking away, pointing towards the distant stars. If the moon had zero rotation, we would eventually see every side of it as it completed a lap around our planet. By the time it finished half an orbit, we would be staring directly at the mysterious far side. But this is not what happens. As the moon travels along its elliptical path, it turns. It turns with agonizing slowness, but it turns nonetheless. For every degree it travels around the Earth, it rotates exactly 1 degree on its axis. It is this 1-to-1 ratio, this perfect matching of two different motions, that keeps the same hemisphere constantly directed toward us. Think of it like walking around a bonfire in a circle while keeping your face constantly turned toward the flames. To keep your eyes fixed on the fire in the center, you must slowly turn your body as you walk. By the time you have completed one full circle around the fire, your body has also made one full rotation. If you had not rotated, you would eventually be facing away from the fire. The moon is doing exactly this. It is pirouetting around the Earth, but the speed of its pirouette matches the speed of its orbit so precisely that the turning is hidden from our view. This phenomenon is known as synchronous rotation. It is not a coincidence, nor is it a matter of luck. It is a profound gravitational state that affects moons and planets all across the galaxy. But before we explore the forces that cause this lock, forces we will explore later in our journey, we must first fully appreciate the motion itself and what it means for the passage of time on our satellite. Because the moon spins so slowly, the concept of a day on the moon is radically different from what we experience on Earth. On our planet, the world spins rapidly, giving us a rhythm of light and shadow that repeats every 24 hours. We are used to the sun rising, crossing the sky, and setting, all within a short period of rest and activity. On the moon, however, the rotation is languid, because it takes the moon roughly 27 days to complete one rotation on its axis, the same amount of time it takes to orbit Earth. A single day on the moon lasts for nearly a month. If you were to stand in the dusty gray plains of the lunar equator, the sunrise would not be a fleeting event of colorful clouds and bird song. It would be a slow, majestic, and silent unveiling of the landscape. The sun would creep over the eastern horizon with agonizing slowness. It would take hours just for the full disk of the sun to clear the jagged lunar hills. Once risen, the sun would not rush across the sky. It would hang there, inching westward day after day. For approximately 14 Earth days, the sun would shine relentlessly, heating the surface to temperatures hot enough to boil water. There is no atmosphere to scatter the light, so the sky remains pitch black even at high noon, with the sun burning like a harsh spotlight against the void. Then, after 2 weeks of continuous daylight, the sun would finally touch the western horizon and sink below it, plunging the world into a freezing night that lasts for another 14 Earth days. This cycle, the lunar day, is the direct result of that slow, synchronous spin. It is proof that the moon is indeed rotating. If it were not spinning, the sun would rise and set at a completely different rhythm, disconnected from the moon's position relative to Earth. There is another way to visualize this rotation, one that dispels the myth of the dark side of the moon. This phrase, popularized by culture and music, suggests that there is a side of the moon that is perpetually shrouded in darkness. But this is not true. Because the moon spins, every inch of its surface eventually receives sunlight. When we see a new moon from Earth, the side facing us is dark, but the far side, the side turned away from us, is bathed in brilliant sunlight. When we see a full moon, the side facing us is lit, and the far side is in the deep freeze of the lunar night. The terminator line, the dividing line between day and night, marches across the entire lunar globe, respecting no boundaries, illuminating the near side and the far side with equal impartiality. The only thing that remains dark to us is our knowledge of what that far side looks like from our backyard telescopes. The moon keeps its back to us, but it does not keep its back to the stars or the sun. This synchronous motion creates a unique and somewhat disorienting experience for a hypothetical observer standing on the moon. If you were an astronaut stationed at a base in the center of the near side, looking up into the sky, you would witness a universe in motion. You would see the sun rise and set over the course of a month. You would see the stars drift slowly across the black dome of the heavens, completing a full circuit every 27 days. The entire cosmos would seem to be rotating around you, just as it does from Earth, albeit much slower. But there would be one object that would refuse to move: the Earth. Hanging in the sky, nearly 4 times larger than the moon appears to us, the Earth would sit motionless. It would not rise, and it would not set. Because the moon's rotation perfectly cancels out its orbital motion relative to the Earth, our planet would remain fixed in a specific spot in the lunar sky. If you were near the lunar equator, the Earth would be directly overhead, a beautiful marble-like jewel suspended in the void. If you were near the lunar poles, the Earth would hug the horizon, forever teetering on the edge but never dipping below it. While the Earth wouldn't move across the sky, it would not be static. You would watch it spin on its own axis, displaying the rapid succession of continents and oceans every 24 hours. You would see the swirling white clouds of weather systems forming and dissolving. You would watch the seasons change the color of the hemispheres, from the green of summer to the white of winter. And you would see the Earth go through phases, just as we see the moon go through phases. When the moon is full to us, the Earth is new, a dark circle to the lunarian observer. When the moon is a crescent to us, the Earth appears almost full, bathing the lunar landscape in a soft, blue Earth light that is much brighter than moonlight. This fixed position of Earth in the lunar sky is the reciprocal effect of the moon's locked rotation. It creates a relationship of permanent attentiveness. The moon behaves like a polite dancer who refuses to break eye contact with their partner, no matter how complex the steps of the waltz become. But why? Why does the universe allow for such a precise synchronization? In a cosmos defined by chaos, collisions, and explosions, why do we find such perfect order in the motion of our nearest neighbor? It is easy to look at this arrangement and assume it is a coincidence, or perhaps a temporary alignment that will drift apart over eons. However, astronomers have found that this is not a rare anomaly. When we look out at the other moons in our solar system, we find that synchronous rotation is the norm, not the exception. The 4 massive Galilean moons of Jupiter, Io, Europa, Ganymede, and Callisto, are all tidally locked to their giant parent planet. They keep the same faces turned toward Jupiter as they race around it. The large moons of Saturn, including Titan, show the same behavior. Even the planet Mercury has been trapped in a gravitational resonance with the Sun, though its dance is slightly more complex. This suggests that the locking of a moon's spin is a fundamental destiny for celestial bodies that orbit close to a larger companion. It is a state of equilibrium, a gravitational resting place that nature seeks out. The moon did not start this way, and it did not choose this orientation. It was forced into it. To understand how a massive sphere of rock weighing more than 70 quintillion tons can be grabbed and forced to stop spinning freely, we have to look beyond the simple geometry of circles and spheres. We have to look at the rock itself. We tend to think of the moon as a solid, unyielding object, a dead stone in the sky. But gravity sees it differently. Gravity sees the moon as something pliable, something that can be stretched, squeezed and molded. The reason the moon keeps its face toward us is not just about motion. It is about friction, energy, and the invisible, relentless grip of the Earth. It is a story of a billions-year-long tug of war that the Earth eventually won. The stillness we see today is actually the aftermath of a dramatic braking maneuver that took place over eons, a process that drained the moon of its rotational energy until it settled into the quiet, locked cadence we observe tonight. As we gaze up at that familiar face, the face of the man in the moon, we are looking at a survivor. We are looking at an object that has been tamed by the Earth's influence. The stillness is not a lack of motion, but a perfect balance of motion. It is a dynamic harmony that hides the violence of the past and the subtle forces that are still at work today. When we observe the moon through a telescope, the sense of stillness is amplified. The shadows inside the craters are ink black and sharp, lacking the softening effect of an atmosphere. The mountains rise abruptly from the lava plains. There is no wind to erode the valleys, no water to smooth the stones. It is a landscape of preservation, where footprints left by astronauts half a century ago remain as crisp as the day they were made. This physical stillness on the surface mirrors the rotational stillness we perceive from Earth. It creates an aura of timelessness, a feeling that the moon has stepped outside the rush of history. But as we will see, this stillness is deceptive. The moon is not merely a passive rock being swung around the Earth. It is an active participant in a gravitational relationship that affects us every day. The same forces that stop the moon from spinning freely are also tugging at our own planet, stretching our oceans, and slowly, imperceptibly, altering the length of our days. The lock is not just a visual curiosity. It is the physical manifestation of a bond that ties the two worlds together. It is a bond made of gravity, but it acts like a physical tether. Imagine a heavy rope connecting the center of the Earth to the center of the moon, keeping them facing each other as they spin. This invisible tether is what we call tidal locking. As we prepare to delve deeper into the mechanics of this locking, let us hold on to the image of the moon as it hangs in the night sky. Let us appreciate the sheer unlikelihood of its appearance. A sphere of gray rock, over 300,000 kilometers away, moving at thousands of kilometers per hour, yet rotating with such exquisite precision that it never reveals its back to us. It is a silent, spinning mystery that requires us to look not just with our eyes, but with our understanding of the fundamental forces that govern the cosmos. The moon is spinning. It is breathing. It is reacting to the Earth. And to understand why it looks so still, we must leave the realm of pure observation and descend into the invisible, heavy, and stretching world of gravity itself. We must understand how the Earth reached out across the void and took hold of the moon, slowing it down until it fell into step with us, creating the eternal gaze of the silent sentinel. To understand why the moon hangs so still in our sky, we must look past the silvery light it reflects and focus instead on the invisible, heavy hand that holds it in place. That hand is gravity. In our daily lives, we tend to think of gravity as a simple, one-way direction. It is the force that pulls a dropped cup to the kitchen floor, or the weight that presses us into our beds at night. We experience it as a uniform blanket that covers everything equally. But out in the deep vacuum of space, where massive worlds dance with one another, gravity behaves with a complexity and a nuance that is far more like a physical touch than a simple downward pull. When the Earth reaches out to the moon, Across the vast emptiness of nearly 400,000 kilometers, it does not pull on every single atom of the moon with the exact same strength. This is the key secret to the moon's motion. Gravity is a force that fades with distance. It is strongest at the source and grows quieter, softer, and weaker the further away you travel. Consider the moon not as a single point in the sky, but as a massive three-dimensional world, a sphere of rock with a front side and a back side. Because the moon is thousands of kilometers wide, the face that looks toward Earth is significantly closer to us than the face that looks away. This difference in distance might seem trivial compared to the vast gap between the two worlds, but in the delicate calculus of orbital mechanics, it is everything. The Earth's gravity pulls harder on the near side of the moon than it does on the center, and it pulls harder on the center than it does on the far side. It is a gradient of force, a gradual lessening of grip as you move from the front of the moon to the back. Imagine holding a soft rubber ball in your hand. If you were to attach a string to the front of the ball and pull, the front would move forward, dragging the rest of the ball with it. But now, imagine that instead of a string, you have a magical force that pulls the front of the ball strongly, the middle of the ball gently, and the back of the ball barely at all. What happens to the rubber ball? It stretches. The front races ahead, trying to fall toward the Earth faster than the middle. The middle tries to fall faster than the back. The result is that the entire moon is pulled taut. It is physically stretched along the line, connecting it to Earth. This stretching force is what astronomers call a tidal force. We are used to hearing the word tides and thinking of the oceans, the rhythmic rise and fall of water along the beach. But tides are not unique to water. Tides affect everything. They affect the atmosphere. They affect the tea in your cup. And most importantly, they affect solid rock. The moon, despite being made of cold, hard stone, is elastic. Under the influence of Earth's differential gravity, the moon does not remain a perfect sphere. It is pulled out of shape. It is molded into a slight oval, something resembling a rugby ball or a lemon, with one pointed end facing towards Earth and the other pointed end facing away into the blackness of space. This distortion is not massive to the naked eye. You would not notice it just by looking up, but physically it creates a bulge of rock that rises up from the lunar surface. This bulge is the handle that Earth uses to control the moon. It is the grip by which our planet tamed its satellite. To see how this grip stopped the moon's spin, we have to perform a mental experiment. We have to wind back the clock and imagine a time when the moon was not locked to the Earth. Imagine the moon spinning rapidly on its axis, pirouetting fast, just like the Earth does today. In this ancient scenario, the moon is rotating quickly, but it is also orbiting the Earth. As it spins, that tidal bulge of rock, that lemon shape created by Earth's gravity, wants to stay aligned with the Earth. Gravity always tries to pull the long axis of the lemon so that it points directly at the source of the pull. The bulge wants to point at us, but because the moon is spinning fast, the rock that forms the bulge is constantly being carried away. The rotation of the moon drags the bulge ahead of the Earth-Moon line. The peak of the raised rock is rotated out of alignment, carried forward by the moon's momentum. This creates a conflict, a cosmic struggle between the momentum of the spin and the pull of gravity. The Earth, sensing that the bulge has drifted out of alignment, reaches out with its gravitational fingers and grabs it. It pulls back on that leading bulge, trying to twist it back into line. This creates a torque, a twisting force, that acts against the moon's rotation. It is exactly like a brake pad pressing against a spinning wheel. The Earth drags on the bulge, and that drag acts as friction. Day after day, year after year, millennium after millennium, this invisible friction worked on the moon. It was a relentless, silent braking maneuver. Every time the moon tried to spin past the Earth, gravity tugged on its protruding waistline, whispering, "Slow down, slow down." This process was not without cost. The energy of that spinning motion had to go somewhere. You cannot simply destroy energy. You can only change its form. As the Earth clamped down on the spinning moon, the energy of rotation was converted into heat. Deep inside the moon, the rock groaned. As the moon spun relative to the Earth, the tidal bulge had to migrate across the surface. The rock was constantly being kneaded, stretched, and compressed. Imagine taking a metal wire and bending it back and forth rapidly. The wire gets hot. The same thing happened to the moon. The solid crust rose and fell, flexing under the strain of the tidal migration. This internal friction generated immense amounts of heat within the lunar interior, dissipating the rotational energy into the cold void as thermal radiation. It was a long, slow surrender. The moon's rotation slowed from a matter of hours to days to weeks. Eventually, the rotation slowed so much that it perfectly matched the time it took for the moon to orbit the Earth. At that precise moment, the bulge finally aligned with the Earth. The lemon shape settled into place, with its long end pointing directly at us. The Earth's gravity continued to pull, but now there was no misalignment. The bulge was exactly where gravity wanted it to be. The torque vanished. The braking stopped. The lock was complete. This is the state we find ourselves in today. The moon still has that bulge, a permanent distortion in its shape, locked in place, pointing eternally at the Earth. It is like a heavy pendulum that has finally stopped swinging and hangs perfectly straight. The gravity of Earth holds that bulge tight, preventing the moon from speeding up or slowing down its rotation. If something were to nudge the moon and make it spin a little faster, the bulge would drift ahead, and Earth would pull it back. If it slowed down, the bulge would lag behind, and Earth would pull it forward. It is caught in a gravitational valley, a place of minimum energy and maximum stability. This invisible grip is profound because it reveals that space is not just an empty stage where objects move freely. It is a web of influences. It is a thick, viscous medium of forces where objects communicate with one another through the language of mass. And while the moon has succumbed to this force, we must remember that gravity is a two-way street. The moon is much smaller than Earth, so it lost the battle of the spin first. But the moon also exerts tidal forces on the Earth. We see this every time we visit the coast. The water in our oceans is fluid and easy to move, so it responds readily to the moon's differential pull. The water on the side of Earth facing the moon is pulled away from the solid planet, creating a high tide. The Earth itself is pulled away from the water on the far side, creating a second high tide on the opposite side of the world. But just as the moon stretches, the solid Earth stretches too. As you lie in bed, the ground beneath your house rises and falls by roughly 30 centimeters twice a day, every day, in response to the moon's passage overhead. You do not feel it because everything around you, the bed, the house, the street, rises and falls with you. The Earth is being kneaded by the moon just as the moon is gripped by the Earth. However, because Earth is so much more massive and because it spins so much faster, the moon's braking effect on us is much weaker. It is happening, but at a pace that is almost imperceptible to the human lifespan. The moon is trying to lock us, just as we locked it. It is dragging on our tidal bulges, trying to slow our 24-hour day into something much longer. But that is a story of the deep future. For the moon, the process is finished. The war is over. The silence we perceive when we look at the moon is the silence of a settled equilibrium. This mechanism of tidal locking explains why the phenomenon is so common throughout the universe. It does not require special conditions or a unique coincidence. It only requires gravity, time, and a little bit of flexibility. Any two objects orbiting close to each other will eventually undergo this dance. The larger partner will always tame the smaller one first. In the case of Pluto and its large moon Charon, they are so close in size that they have already tidally locked each other. If you stood on Pluto, Charon would always be in the same spot in the sky. If you flew to Charon, Pluto would hang frozen in the heavens. They face each other like two dancers spinning while holding hands, looking only into each other's eyes. Our moon is solitary in its gaze. It looks at us while we continue to turn, displaying all of our faces, Asia, Europe, the Americas, the Pacific, to its unblinking watch. This understanding of tidal forces changes how we view the moon's surface. When we see the cratered highlands and the dark Maria, we are looking at a crust that has been stiffened and frozen into a shape dictated by Earth. The very sphere of the moon is a monument to Earth's influence. It is not a perfect geometric ball. It is a distorted echo of our planet's mass. It is fascinating to consider how much energy was drained from the moon to achieve this state. The rotational energy of a spinning world is immense. It is the energy of billions of tons of rock moving at hundreds of kilometers per hour. All of that energy was bled away through the friction of the tides. It radiated out into the universe as heat, invisible infrared light that drifted away from our solar system billions of years ago. The stillness of the moon is the absence of that energy. It is a world that has been brought to rest by the sheer persistence of Earth's gravity. If you could see gravity, the night sky would look very different. You would not just see the white glow of the moon. You would see a vast, funnel-shaped depression in the fabric of space around the Earth. You would see the moon rolling along the rim of this funnel, and connecting them, you would see the tension, the stretching lines of force that keep the moon's heavy face pointed inward. It is a relationship of intimacy and control. The Earth keeps the moon on a leash, but it is a leash made of geometry and curvature. There are times, however, when this grip seems almost too perfect to be believed. How could a chaotic process result in such a precise match, down to the second? The answer lies in the self-correcting nature of the mechanism. As mentioned before, if the moon were to drift out of sync, the forces would immediately increase to bring it back. It is a stable trap. Once a moon falls into a tidal lock, it is incredibly difficult to get out. It would require a massive impact, something colossal enough to spin the world up again, to break the hold of the tidal forces. Without such a cataclysm, the moon will remain locked to us forever. As long as it orbits Earth, it will face Earth. It has no choice. The grip of tidal forces is patient. It is weak over short distances, but over the scale of planets and eons, it is absolute. So, the next time you see the moon rising over the treetops, looking exactly the same as it did the night before, and the night before that, remember the invisible struggle that took place to create that view. Remember the stretching of the rock, the heating of the crust, and the slow, grinding deceleration that tamed a spinning world. The moon is not still because it is dead. It is still because it is held. It is caught in the invisible, loving, and crushing grip of our own home planet. This interplay of forces did not happen overnight. It was not a sudden event where the moon slammed on the brakes. It was a process that unfolded over a timeline so vast it challenges the human ability to comprehend. To fully appreciate this history, we must travel back to the very beginning. We must go back to a time before the lock, before the tides, and even before the moon as we know it existed. We must witness the violent birth of our companion and the chaotic, rapidly spinning era that preceded the great slowdown. To fully comprehend the silence of the moon, we must first confront the noise of its creation. The stillness we observe tonight is not the natural state of things, but rather the aftermath of a cosmic trauma that occurred so long ago that the Earth itself has healed all its scars. We have to cast our minds back into the deepest reaches of time. We must travel back 4.5 billion years to an era known as the Hadean Eon. If we were to look for our home in this ancient epoch, we would not find the blue and green marble we know today. There were no oceans, no forests, and no ice caps. There was only fire. The young Earth was a sphere of molten rock, a glowing ember drifting through the dusty darkness of the early solar system. At this time, the Earth was alone. It had no companion. It spun solitary and unaccompanied, a lonely wanderer in the dark. But the solar system of 4.5 billion years ago was a crowded, chaotic shooting gallery. It was filled with planetary embryos, large, half-formed worlds that were jostling for space, crossing paths, and competing for the material that circled the infant sun. One of these wanderers, a protoplanet roughly the size of Mars, was on a collision course with our world. Astronomers have given this lost planet the name Theia, named after the mother of the moon in Greek mythology. The encounter was not a glancing blow. It was a cataclysmic merging. Theia slammed into the young Earth with a force that defies human comprehension. It was an event so energetic that it nearly tore our planet apart. The collision liquefied the crust and sent a spray of molten debris exploding outward into space. Trillions of tons of rock, magma, and vapor were cast into orbit, forming a blazing ring around the Earth. For a brief period, our planet looked less like the Earth we know and more like Saturn, a burning sphere surrounded by a disk of incandescent dust. It was from this ring of fire that our moon was born. Gravity, the great sculptor of the cosmos, immediately went to work on the debris field. The dust and rock began to clump together, colliding and sticking, gathering mass with voracious speed. Some computer simulations suggest that the moon may have assembled itself in a startlingly short amount of time, perhaps as little as a few years or even a few months. From the chaos of the ring, a new world emerged, but this infant moon was nothing like the silver lantern we see tonight. It was a terrifying, beautiful monster. It was roughly 15 to 20 times closer to Earth than it is today. If you could have stood on the cooling skin of the Hadean Earth, wearing an indestructible suit to survive the heat, and looked up, your view would have been dominated by the moon. It would have filled a massive portion of the sky, looming like a colossal glowing red eye. It was so close that you could have seen the churning lakes of lava on its surface with your naked eye. It was a world of fire orbiting Oradsai, world of fire, and it was fast. In this early epoch, everything was moving with a frantic, youthful energy. The Earth was spinning incredibly fast, completing a full rotation in just 4 or 5 hours. The The sun would rise and set in a dizzying blur. The moon, too, was spinning wildly on its own axis. It was not tidally locked. It was a free rotating body, turning its face away from Earth again and again, revealing every side of itself to its parent planet. There was no man in the moon back then. There were no calm gray seas. There was only a rapidly shifting molten sphere, spinning and tumbling as it raced around the Earth at a breakneck speed. It orbited the Earth not in 27 days, but in perhaps 10 hours. It was a time of extreme dynamism, a violent ballet of two molten worlds dancing cheek to cheek. However, this proximity came with a price. The forces of gravity we discussed earlier, the tidal forces, were not the gentle tugs they are today. They were violent, crushing waves. Because the moon was so close, its gravity grabbed hold of the molten Earth with immense power. It raised tides of magma that were kilometers high. As the Earth spun beneath the moon, these colossal waves of liquid rock would crash across the surface of our planet, a tsunami of lava driven by the passage of the satellite overhead. And the Earth, in turn, grabbed the moon. The tidal bulge raised on the moon was extreme, stretching the little world into a pronounced football shape. It was this intense interaction that began the great slowdown. The laws of physics demand balance. There is a fundamental rule in the universe known as the conservation of angular momentum. It states that the total amount of spin in a closed system must remain constant. If one part of the system slows down, another part must speed up or move further away to compensate. The Earth was spinning faster than the moon was orbiting. Because of this, the tidal bulge that the moon raised on Earth was constantly being dragged ahead of the moon. The Earth's rapid rotation pulled the mountain of water and rock forward, keeping it slightly ahead of the satellite's position. This created a gravitational lasso. The bulge on Earth pulled the moon forward, adding energy to its orbit. When you add energy to an orbiting object, it moves higher. It seeks a wider path. So, inch by inch, the moon began to drift away. As the moon stole energy from Earth to push itself outward, the Earth paid the price. It slowed down. The friction of those magma tides acted as a brake on our planet's day. The 4-hour day became a 6-hour day, then a 10-hour day. The Earth was spinning down, transferring its rotational momentum into the moon's orbital distance. Simultaneously, the moon was undergoing its own dramatic transformation. While it was pushing itself away from Earth, the Earth's gravity was mercilessly breaking the moon's own rotation. Because the moon is much smaller than Earth, with only about 1% of Earth's mass, it lost its rotational battle very quickly in astronomical terms. Within perhaps just 10 to 20 million years after its formation, a blink of an eye in the lifespan of the solar system, the moon's rapid spin had been crushed. The friction of the Earth's grip had drained the moon of its independent rotation. The wild tumbling ceased. The moon settled into that synchronous lock we see today. This happened when the moon was still very young and likely still partially molten. Imagine the drama of that final locking event. The moon, a glowing, cooling sphere, slowing its spin until one hemisphere was permanently captured by Earth's gravity. The man in the moon was not yet there. The great lava basins had not yet formed, but the face was set. The dance had been simplified. From that moment on, the moon never looked away. But even though the spin was locked, the retreat continued. The moon kept moving away, driven by the tides of Earth's oceans. Over hundreds of millions of years, the moon drifted from 20,000 kilometers away to 100,000, then 200,000. As it moved away, its apparent size in our sky shrank. It went from a sky-swallowing behemoth to a large companion, and finally to the modest quarter-coin-sized disk we see today. The glowing red lava on its surface cooled and hardened into a black, crusty shell. The light of the moon shifted from its own internal incandescence to the cool, reflected silver of sunlight. This history of violence and migration explains a profound mystery about the moon's influence on life. We often think of the moon as a passive observer, but its history is deeply intertwined with ours. If the moon had not formed so close, and if it had not moved away, the Earth would be a very different place. The rapid spin of the early Earth would have created fierce winds and violent storms that would have scoured the surface for billions of years. By stealing our spin and moving away, the moon calmed our planet. It lengthened our day from a frantic few hours to a leisurely 24. It gave the sun time to warm the mornings and the evenings to cool the land. It created the rhythm of time that biology would eventually adopt. The Great Slowdown was not just a mechanical event, it was a terraforming event. The moon sacrificed its own rotation and drifted into the lonely dark to purchase a stable environment for the Earth. We can still see the evidence of this ancient retreat written in the geological records of our own planet. Scientists studying ancient tidal sediments, layers of sand and silt laid down by tides billions of years ago, have found proof that the days were shorter in the past. These tidal rhythmites show patterns that indicate a year contained over 400 days, meaning each day was significantly shorter than 24 hours. The moon was closer then, the tides were stronger, and the Earth was spinning faster. It is a humbling realization that the moon is continuously leaving us. Even tonight, as you sleep, the moon is creeping away. It is moving away from Earth at a rate of roughly 3.8 centimeters per year, about the same speed that fingernails grow. It is a tiny distance, barely noticeable over a human lifetime, but multiply that by millions of years, and it is a vast journey into the void. The lock, however, remains. The moon moves further away, but it remains faithful in its orientation. It is like a dancer who is slowly backing away from their partner across the ballroom floor, but refuses to break eye contact. The connection is stretched, but it is not broken. There is a poignant beauty in this history. We started as two molten, chaotic worlds, crashing and spinning in a violent embrace. We were too close, too hot, and too fast. Through the long patience of gravity, we have reached a middle age of stability. The fires have cooled. The magma oceans have solidified into rock and water. The frantic spinning has slowed into a measured waltz. The moon we see tonight is the veteran of this great migration. Its stillness is the result of a long, hard-fought battle against momentum. It is a monument to the energy that was dissipated to bring peace to the Earth-Moon system. When you look at the full moon, you are looking at an object that has traveled nearly 400,000 kilometers to get to where it is. You are looking at a face that was frozen in place when the solar system was still just a nursery of dust. The craters you see, Tycho, Copernicus, Plato, were smashed into that face long after it had already locked its gaze on us. They are the scars accumulated during a billions of years' stare. This journey from a violent birth to a quiet present sets the stage for the subtle complexities that remain. The moon is locked, yes, it is still, yes, but it is not dead. The connection between Earth and moon is dynamic. Even though the moon keeps the same face toward us, it does not stand perfectly rigid. It breathes, it nods, it teeters. As we will see next, the perfect lock is not quite perfect. The moon has a few secrets left to reveal about its motion. It allows us, if we are patient and observant, to peek around the edges. It allows us to see just a fraction more than we should. This phenomenon, a gentle swaying of the silent sentinel, proves that the dance is still ongoing, subtle and slow, in the quiet gravity of the night. But for now, let us rest in the knowledge of how far we have come. From the fire of the collision to the cool silence of the present orbit, the moon has been our constant, evolving companion. It spun wildly, so that we might one day spin slowly. It drifted away, so that we might have calm seas. It is the silent guardian that absorbed the chaos of the early solar system, leaving us with the peaceful, rhythmic night we enjoy today. If you were to take a high-quality photograph of the full moon tonight, and then compare it to a photograph taken exactly 1 month from now, and then another 6 months later, you would notice something unsettling. At first glance, the images would look identical. The man in the moon would be staring back at you. The dark seas would be in their familiar places, and the bright crater Tycho would be anchoring the southern highlands. But if you overlaid these images on a computer screen and played them back as a high-speed movie, the stillness would vanish. The moon would not look like a stone frozen in space. It would look like a living, restless thing. It would appear to be breathing. It would rock gently from side to side, shaking its head no. It would nod up and down, tipping its chin yes. It would roll slightly, like a boat caught in a gentle swell on a calm lake. Through this complex, rhythmic swaying, features near the edge of the lunar disk would roll into view and then vanish again into the darkness behind the horizon. This phenomenon is known as libration. It is the subtle, secret motion of the moon that defies the perfect lockdown we described earlier. While tidal forces have indeed trapped the moon's rotation, they have not pinned it down completely. The lock is secure, but it is not rigid. It has a little bit of play in it, a little bit of cosmic wiggle room that allows the moon to dance within its constraints. Because of this gentle breathing motion, we do not see merely 50% of the lunar surface, as simple geometry would suggest. Over the course of time, the moon reveals a little bit more of its hidden self. It allows us to peek around the edges, granting us a view of nearly 59% of its total surface area. It is a tease, a celestial game of peekaboo that has allowed astronomers to map the fringes of the far side long before the first rocket ever left the atmosphere. To understand why the moon breathes like this, we have to look at the shape of its path around the Earth. We often draw orbits as perfect circles, but nature rarely draws perfectly round lines. The moon's orbit is an ellipse, a slightly stretched out circle, an oval. This means that the moon's distance from Earth is not constant. There are times in the month when the moon swings in close to us, a point known as perigee. At perigee, the moon is merely 363,000 kilometers away, looming large and bright. 2 weeks later, it swings out to its furthest point, known as apogee, drifting out to over 405,000 kilometers. The moon is constantly diving in and pulling away, pulsing in size as it circles us. This changing distance is the engine of the first type of swaying, known as libration in longitude. There is a fundamental law of planetary motion discovered centuries ago, which dictates that objects in orbit move faster when they are closer to the parent body and slower when they are further away. It is like a figure skater pulling in their arms. As the moon approaches perigee, gravity whips it around the Earth with extra speed. It races through that part of its orbit. But when it climbs out to the distant apogee, it slows down, lingering in the outer reaches like a tired runner at the top of a hill. However, the moon's rotation, its spin on its own axis, does not change speed. The moon is a massive, heavy flywheel of rock. It has a tremendous amount of inertia. It cannot speed up its spin or slow it down on a whim. It rotates at a steady, constant, metronomic pace, turning exactly once every 27.3 days. It is a reliable clock. And this is where the mismatch happens. This is where the dance gets interesting. Imagine a race car driver on a circular track. The car represents the orbital motion of the moon, and the driver's head represents the rotation. If the driver turns his head at a perfectly constant speed to watch the crowd in the center infield, everything works fine as long as the car maintains a constant speed. But if the car suddenly accelerates down the straightaway, the driver's head turn will lag behind. He won't turn his head fast enough to keep his eyes on the center. For a moment, he will be looking slightly backwards relative to the track. This is exactly what happens to the moon. When it swings close to Earth and speeds up in its orbit, its rotation cannot keep up. The moon physically moves along its path faster than it spins. As a result, the face of the moon lags behind. It fails to turn quite enough to keep pointing directly at us. Because of this lag, we get to peek around the western edge of the moon. We see a sliver of the far side that is usually hidden. Then, the situation reverses. As the moon drifts out to its furthest point, its orbital speed slows down dramatically. It becomes sluggish. But the spin continues at its steady, constant rhythm. Now, the rotation is too fast for the orbit. The moon over-rotates. It turns its head further than necessary. This allows us to peek around the eastern edge of the moon. Month after month, this cycle repeats. The moon races ahead and lags behind, shaking its head left and right in a slow, rhythmic denial. It allows us to see features like the Mare Orientale, a spectacular bullseye impact basin that sits right on the edge of the visible world. Sometimes it is visible, a dark sliver on the rim. Other times it rotates completely out of view, hidden by the sway. But the moon does not just shake its head no, it also nods yes. This second motion, known as libration in latitude, comes from the way the moon sits in space. The moon does not orbit the Earth perfectly level with our equator. Its orbit is tilted, inclined by about 5 degrees. Furthermore, the moon's own spin axis, the imaginary pole it rotates around, is tilted slightly, almost perpendicular to its orbit. This geometry means that as the moon travels around us, it sometimes dips below the Earth's waistline and sometimes rises above it. It is like a person sitting in a chair while a friend walks around them. If the friend stands on a step stool, the seated person can see the top of their head. If the friend crouches down, the seated person can see under their chin. When the moon climbs to its highest point, north of the Earth's orbital plane, we look up at it and see underneath its southern pole. We can look past the usual bottom edge of the disk and see crater floors and mountains that are normally obscured. 2 weeks later, when the moon dives below the plane, we look down onto its northern pole. This nodding motion is gentle, a slow, vertical rocking that takes a month to complete. It gives the moon a three-dimensional quality. It reminds us that it is a sphere, not a flat plate. Observing the polar regions during these favorable librations allows astronomers to see sunlight catching the peaks of eternal light, mountains at the lunar poles that are almost always illuminated, and the deep, shadowed craters that may hold ancient ice. There is even a third, subtler wobble, one that has nothing to do with the moon's motion and everything to do with ours. It is called diurnal libration, and it is caused by the rotation of the Earth itself. The Earth is a large platform, roughly 12,700 kilometers wide. If you stand on the surface of the Earth, you are not at the center of the universe. You are riding on the edge of a spinning carousel. When you watch the moon rise in the east, you are standing on the leading edge of the Earth. You are peering around the curvature of the planet to see the moon come up. This position gives you a slightly different angle, a few fractions of a degree, than if you were viewing the moon from the center of the Earth. You can see a tiny bit more of the moon's upper eastern edge. 12 hours later, when the moon sets in the west, the Earth has carried you to the other side of the platform. You are now looking back at the moon from a completely different vantage point, separated by thousands of kilometers from where you started. This shift in perspective allows you to see a tiny bit more of the moon's other edge. It is a small effect, barely a degree of difference, but it adds to the complexity of the view. It means that throughout a single night, as the moon arcs across the sky, our perspective on it is constantly shifting. We are bobbing our heads side to side, trying to see around the corner. When you combine all these motions, the east-west speed wobble, the north-south tilt nod, and the daily parallax of the observer, the result is a complex, spiraling dance. The center of the moon's face is not a fixed point. It traces a small, wobbly circle in the sky over the course of the month. This breathing of the lunar sphere has profound implications for the environment on the moon itself. We tend to think of the line between day and night, the terminator, as a steady, marching shadow. But because of libration, the sun does not rise and set in exactly the same place on the horizon every month for every location. There are strange, twilight zones on the edges of the moon. These are regions that belong neither fully to the near side nor fully to the far side. They are the borderlands. In these areas, the Earth does not hang motionless in the sky as it does elsewhere. If you stood in this libration zone, you would see the Earth rise slowly above the horizon, hover there for a few days, bobbing up and down, and then sink back down below the ground. You would experience Earth rises and Earth sets, a phenomenon that is impossible on the central meridian of the near side. These edge regions are some of the most fascinating landscapes on the satellite. They are places of transition. They are the only places on the moon where you could theoretically act as a bridge between two worlds, standing with 1 foot in the realm of the Earth-gazers and 1 foot in the realm of the eternal void. For centuries, map-makers struggled with these regions. They would draw the moon, but the edges would be fuzzy, distorted, and constantly changing. A crater that was visible 1 week would be gone the next. Mountains would change their profile as the perspective shifted. It wasn't until the age of photography and consistent monitoring that the full extent of the visible moon was catalogued, revealing that 59% slice of the pie. But this motion also serves as a reminder of the elasticity of gravity. The moon is trying to follow a straight line, trying to spin at its own pace, but the Earth is constantly correcting it. The libration is the visual evidence of the tension between momentum and gravity. It is the vibration of the string that holds the two worlds together. It is soothing to think of the moon this way, not as a rigid, staring eye, but as a rocking cradle. The motion is slow, taking weeks to complete a single cycle. It is a rhythm that is almost too slow for us to perceive, yet it is real. It is a cosmic lullaby, a gentle swaying that has continued for billions of years and will continue for billions more. The libration also tells us that the tidal locking process we discussed earlier is a dynamic state. The moon is settled, yes, but it is still responding to the laws of Kepler and Newton. It is obedient, but it has its own character. It creates a relationship that is slightly imperfect, slightly asymmetrical, which makes it all the more beautiful. If the moon were in a perfectly circular orbit with zero tilt, it would be dead still. It would be a frozen photograph. The imperfections of reality, the oval orbit, the tilted axis, are what give the moon its life. This wobbling has practical consequences for future explorers as well. If we were to build a radio telescope on the far side of the moon, to shield it from the noisy radio chatter of Earth, we would have to place it deep into the far side. We could not place it just over the ridge. If we placed it too close to the edge, the libration of the moon would occasionally rock the Earth into view, blasting the sensitive instruments with our radio broadcasts. The quiet zone of the moon is determined by the maximum sway of this libration. So, the moon keeps its secrets, but not all of them. It holds back 41% of itself, a region that remains forever invisible to the earthbound observer. No matter how much the moon rocks, no matter how much it nods, that 41% never comes into view. It is the true dark continent of our solar system, a place that was mapped only by the imagination until the space age began. As we watch the moon sway in the sky, we are reminded that our perspective is limited. We are stuck on one planet, looking out at another. We see the face, the smile, the scars. We see the breathing of the sphere, but we are denied the other half of the story. This leads us to the inevitable question: what is back there? What is hidden behind the curtain of the lunar horizon? Is the other side just a mirror image of the side we know? Does it have the same dark seas, the same man in the moon, the same familiar geography? For thousands of years, humanity could only guess. Some thought it might be a paradise of atmosphere and water, hidden from our view. Others thought it was a hollow shell. The truth, as revealed by the first grainy images sent back by robotic probes, was far more shocking and far more mysterious than anyone had anticipated. The side of the moon that turns away from us, the side protected by the moon's own body from the gaze of Earth, is a different world entirely. It does not look like the moon we know. It is a battered, rugged, and ancient place, devoid of the seas that define our night sky. As the moon rocks back and forth, offering us tantalizing glimpses of the crater rims on the edge, it invites us to travel further, to leave the safety of our visual tether and fly around the bend, to see the moon not as a flat disk, but as a complete, complex, and divided world. The breathing of the moon is the final clue that the relationship between Earth and moon is one of deep physical distortion. And as we leave the comfort of the near side, we must prepare ourselves for a landscape that has been shaped by its isolation, a landscape that faces the universe alone. For the vast majority of human history, the far side of the moon was not a place, but a concept. It was a blank canvas upon which we projected our wildest fantasies. Because the moon's synchronous rotation locked it so tightly in place, dragging it around the Earth with one face permanently averted, the far hemisphere remained the ultimate forbidden territory. It was physically closer to us than the city of London is to New York, yet it was more inaccessible than the distant stars. Philosophers and astronomers argued over what lay hidden in that blind spot. Some believed it was a mirror image of the side we could see. populated by the same dark, flat seas and bright highland craters. Others, letting their imaginations roam into the realm of science fiction, speculated that the far side might hold an atmosphere, trapped in the valleys, perhaps supporting vegetation, or even cities of selenium inhabitants, forever hiding from the prying eyes of Earth. It was a mystery that felt personal, as if the moon were deliberately keeping a secret from us. The veil was finally lifted on a quiet day in October 1959. The Soviet spacecraft Luna 3, a primitive tin can of electronics by modern standards, swung around the back of the moon. It was a moment of profound technological audacity. As the probe drifted into the radio shadow of the moon, cutting off contact with Earth, its camera began to click. It snapped a series of grainy, noisy photographs on actual film, developed them on board in a miniature chemical lab, and then scanned the images to beam them back across the void once it re-emerged. When those first images flickered onto the screens in the control room, the scientists were baffled. They expected to see the familiar man in the moon, or at least a similar arrangement of dark lava plains. Instead, they saw a stranger. The face revealed in those photographs was almost unrecognizable. It was a rugged, battered, and monochrome world. The dark seas that define the near side, the ocean of storms, the sea of tranquility, the sea of serenity, were almost completely missing. In their place was a chaotic, jumbled landscape of endless craters. It looked like a piece of dough that had been pummeled by 1,000 fists. It was a scarred, pock-marked highland that stretched from pole to pole, broken only by a few tiny, isolated splashes of dark darkness. The discovery sent a shockwave through the scientific community. It revealed that the moon was not a uniform sphere. It was a two-faced world. The side facing Earth was smooth, dark, and decorated with vast plains of frozen lava. The side facing the galaxy was rough, bright, and ancient. This dichotomy, known as the lunar asymmetry, became one of the greatest puzzles of the space age. Why would a single world, formed from the same cloud of debris, look so radically different on its two halves? To understand this, we must look at the moon not as a finished sculpture, but as a geologically active body freezing in the dark. We must look at the crust, the outer skin of the moon, and measure its thickness. Gravity data collected by later missions revealed the answer. The crust on the far side of the moon is significantly thicker than the crust on the near side. It is a heavy, armored shell, tens of kilometers deeper than the thin skin that faces Earth. This difference in thickness is the key to the missing seas. Billions of years ago, the solar system was a violent shooting gallery. This period, known as the Late Heavy Bombardment, saw the inner planets being pelted by asteroids and comets left over from the formation of the planets. The moon, having no atmosphere to protect it, took a beating. Massive space rocks slammed into its surface, excavating craters hundreds of kilometers wide and fracturing the crust down to the mantle. On the near side, where the crust was thin, these impacts were like stones thrown through a pane of glass. They punched right through the solid lid of the moon. Beneath the crust lay a mantle still rich with molten rock, or magma. When the asteroids cracked the thin crust, this magma welled up from the deep, bleeding out onto the surface like a wound. It flooded the low-lying impact basins, spreading out into vast, flat lakes of liquid fire. Over millions of years, these lakes cooled and solidified into dark, iron-rich basalt. These are the Maria, the seas. They are not oceans of water, but oceans of rock. They buried the ancient craters, smoothing out the landscape and creating the dark patches that our ancestors would one day interpret as a face. But on the far side, the story was different. When the great asteroid struck the far hemisphere, they hit a fortress. The crust there was so thick, so robust, that the impacts could not punch all the way through to the molten interior. They cracked the surface, yes. They gouged out deep basins and threw mountains of debris into the sky. But they did not trigger the volcanic bleeding. There was no upwelling of lava to fill the scars. As a result, the far side retains the record of every blow it ever took. It is a saturation cratered landscape, meaning that if a new meteor hits it, it must destroy an old crater to make a new one. It is a pristine museum of cosmic violence, unpaved by the smoothing action of volcanism. But this explanation only pushes the mystery one step deeper. Why was the crust thicker on the far side in the first place? Why was the moon lopsided? The answer brings us back to the heat and the lock. We return to the image of the young, glowing Earth and its newly formed companion. Shortly after the moon formed, it was tidally locked to the Earth, just as we described. It stopped spinning relative to us very quickly. At this time, the Earth was extremely hot, a molten ball radiating temperatures of over 2,500 degrees Celsius. It shone in the lunar sky like a second sun, a colossal furnace that never set. Because the moon was locked, one face was constantly bathed in this intense heat from the Earth. The near side was cooked by the glowing planet below. This extra heat kept the near side crust molten and soft for much longer. It prevented the minerals from condensing and freezing into a thick lid. It was kept warm, thin, and pliable by the fires of Earth. The far side, however, faced away from this furnace. It looked out into the freezing cold of deep space. Without the heat of the Earth to keep it warm, the far side cooled down much faster. Elements like aluminum and calcium condensed out of the magma ocean, floating to the top to form a thick, hard crust of rock called anorthosite. So, while the near side was still a slushy, semi-molten soup, the far side was already building its armor. It thickened and hardened, building up a shell that would eventually become impenetrable to the volcanic plumbing below. The two-faced nature of the moon is a direct scar left by the heat of the young Earth. The moon is lopsided because it spent its infancy huddled too close to a fire. This thick crust has hidden many secrets until very recently. For decades, the far side was mapped only from orbit. It was a place seen through the window, but never touched. That changed in January 2019, when the Chinese spacecraft Chang'e 4 made the first ever soft landing on the far hemisphere. It touched down in the von Karman crater, a deep depression inside an even larger structure known as the South Pole Aitken Basin. This basin is one of the largest impact craters in the entire solar system. It is a hole in the moon so wide that it stretches nearly 2,500 kilometers across and 13 kilometers deep. If this impact had happened on Earth, it would stretch from London to Athens. The landing revealed a landscape that felt profoundly alien, even compared to the Apollo sites. The terrain was rugged and rolling, covered in a gray regolith that had been churned by billions of years of impacts. But the most striking feature of the landing site was not the rocks, it was the sky. If you were to stand next to the lander on the far side of the moon, you would experience a sensation that no human has ever truly felt: total isolation from Earth. On the near side, even in the dead of lunar night, the ground is never truly dark. The Earth hangs overhead, shining 50 times brighter than the full moon does on Earth. It casts a blue, ghostly light over the mountains, strong enough to read a book by. It is a constant reminder that home is just right there. But on the far side, the sky is black. The earth is gone. It is blocked by 3,000 kilometers of solid rock beneath your feet. During the lunar night, when the sun is also on the other side, you are plunged into a darkness that is absolute. It is a darkness deeper than any cave on earth. Above you, the stars would shine with a brilliance that is piercing. Without the glare of earthlight to wash them out, the Milky Way would look like a solid river of diamond dust arching from horizon to horizon. You would see the universe as it truly is, uncensored, unpolluted by the light of civilization. This isolation makes the far side the quietest place in the solar system, not just in terms of sound, but in terms of radio waves. On Earth, we are constantly broadcasting. Television signals, radio stations, GPS satellites, military radar, and mobile phone networks fill the air with a cacophony of electromagnetic noise. This noise leaks out into space, creating a bubble of chatter around our planet that makes it very difficult for astronomers to listen to the faint whispers of the early universe. But the moon acts as a shield. The massive body of the moon blocks all that noise. The far side is a radio-quiet zone. It is the only place where we can build telescopes to listen to the very lowest frequencies of radio waves, the ancient signals left over from the dark ages of the universe before the first stars ignited. In this silence, the far side feels like a temple to the cosmos. It is a place that has turned its back on the drama of life on Earth to face the infinite. Yet, despite its thick crust and lack of seas, the far side is not completely dead. The South Pole Aitken Basin shows signs that the impact was so massive it almost melted the crust entirely. There are subtle hints of thorium and other heat-producing elements that suggest the interior was once churning. And recent discoveries suggest that there may be water ice hidden in the deep, permanent shadows of the craters near the poles, craters that are technically on the far side of the dividing line. This water is the legacy of comets that struck the moon eons ago. On the sunlit plains, the water would have boiled away instantly. But in the deep holes at the bottom of the world, where the sun never shines, the ice has remained trapped for billions of years, preserved by the cold. It is a hidden treasure chest that awaits future explorers. The far side also changes our understanding of the moon's role as a guardian. Because it faces away from us, it acts as a shield. For billions of years, the far side has absorbed impacts that might have otherwise grazed the moon and headed for Earth. Or at least, it shows us the density of debris that Earth itself has had to endure. When we look at that battered hemisphere, we are looking at a record of the shrapnel that was flying through our neighborhood. The moon took those hits. It wears the scars so we don't have to. There is a distinct psychological weight to the far side. The Apollo astronauts who orbited the moon, the first humans to ever see this terrain with their own eyes, spoke of the profound loneliness they felt when their craft slipped behind the lunar limb. For 45 minutes during every orbit, they were cut off from all contact with Houston, all contact with their families, all contact with humanity. They were the most solitary human beings who had ever lived. Alfred Worden, the command module pilot for Apollo 15, described floating alone in the shadow of the far side while his colleagues were on the surface. He said, "I am alone now, truly alone and absolutely isolated from any known life. I am it. If account were taken, the score would be 3 billion plus 2 over on the other side of the moon, and 1 plus God knows what on this side." But he also described a sense of peace. The far side was not hostile, it was indifferent. It was the universe existing without us, a vast, silent machine of rock and gravity that did not care about the politics or the wars or the noise of the blue planet it orbited. This indifference is what makes the far side so captivating. It is the moon's wild side. The near side has been tamed by our gaze, named by our map makers, and flagged by our explorers. We have projected our culture onto it, but the far side remains largely untouched, a wilderness of gray peaks and black valleys. As we continue to explore, sending rovers and eventually humans to this hidden hemisphere, we are not just exploring a different location. We are exploring a different history. We are walking on a crust that cooled in the dark. We are drilling into rock that has never felt the warmth of earthshine. The mystery of why the moon doesn't spin, visually solved on the near side. We see the same face, but the consequence of that non-spin is physically felt on the far side. The locking of the moon created two separate worlds on one body. It created a world of heat and lava facing us, and a world of cold and ice facing away. The silence of the far side is heavy. It is the silence of a door that has been locked for 4 billion years, and now that we are prying it open, we are realizing that the lock was there for a reason. It was the result of a thermal dance between a parent and a child, a dance that shaped the very geology of the world we thought we knew. But even this battered shield, this thick-crusted fortress, is not the end of the story. The moon is moving, the earth is slowing. The relationship that created the far side and the near side is not frozen in time. It is evolving. The moon is currently retreating, pulling away from us into the dark. But what is the ultimate end game? Where does this dance lead? If we fast forward the clock, past the era of humans, past the era of the continents, and into the deep, dying light of the future solar system, we find that the moon has one final destiny waiting for it. A destiny where the stillness we see tonight will be mirrored by the earth itself. A time when the rotation of our own world will succumb to the same forces that tamed the moon. A future where the earth and moon will face each other, locked together in a perpetual, unblinking stare, turning together in the dark. As we reach the end of our journey, we must turn our gaze from the ancient past and the silent present toward the deep, distant future. We have seen how the earth tamed the moon, reaching out with invisible gravitational fingers to halt its spin and lock its face toward us. We have seen how the moon breathes and sways, a testament to the lingering energy of its orbit. But the story of the earth and the moon is not finished. It is currently paused in a long, slow middle chapter, but the final pages have yet to be written. There is a profound symmetry waiting in the dark, a destiny that physics has ordained for our two worlds. The lock is currently one-sided. The moon looks at Earth, but Earth continues to spin, showing all its sides to the moon. However, gravity is a conversation, not a monologue. Just as the Earth slowed the moon down, the moon is currently, relentlessly, and patiently slowing the Earth down. The mechanism for this future stillness is the same one that shaped the past, the tides. Every day as the Earth rotates beneath the moon, the gravity of our satellite drags two great bulges of water across the surface of the planet. These are the ocean tides. But because the Earth spins much faster than the moon orbits, turning once every 24 hours compared to the moon's 27 days, these bulges of water are dragged ahead of the moon. They crash into the eastern edges of continents. They scrape across the shallow seabeds of the continental shelves. and they churn through the narrow straits of the world. This constant movement of water creates friction. It is a colossal, planetary-scale braking system. The energy required to drag trillions of tons of water around the globe every day has to come from somewhere, and it comes from the Earth's rotation. The moon is stealing our spin. It is happening with agonizing slowness. The day is getting longer by roughly 2 milliseconds every century. This seems negligible to us as we rush through our lives, but to the cosmos, which measures time in billions of years, it is a steady, unstoppable decline. If we could fast forward the clock, we would see the 24-hour day stretch into 25, then 30, then 40 hours. The sun would linger in the sky for longer and longer periods. The nights would stretch into long, cold vigils. As the Earth slows, the laws of physics demand a trade. The angular momentum lost by the spinning Earth is transferred to the Moon, pushing it into a higher, wider orbit. The Moon is retreating from us, drifting deeper into the void. This retreat leads to a poignant milestone in the future of our sky. There will come a time, roughly 600 million years from now, when the Moon will have moved far enough away that it will no longer appear large enough to cover the Sun. The phenomenon of the total solar eclipse, the breathtaking spectacle where the Sun's corona flares out like a halo around the black disk of the Moon, will vanish forever. Future observers on Earth will only ever see ring-shaped eclipses where the Sun remains a bright annulus around the silhouette of the tiny, distant Moon. We are living in a privileged era, the only time in the history of the planet where the two disks match perfectly. But the process will continue long after the eclipses are gone. The Moon will keep retreating, and the Earth will keep slowing. If we look far enough ahead, billions of years into the future, we can envision the ultimate end state of this system. It is a state known as double tidal locking, or mutual synchronization. In this distant era, the Earth's rotation will have slowed so much that it will match the orbital period of the Moon exactly. The day will no longer be 24 hours long. It will be roughly 47 current days long. The sun would rise and stay in the sky for over 3 weeks, scorching the land, before setting for a 3-week night of freezing darkness. But the most dramatic change would be the position of the Moon. In this future world, the Moon would stop rising and setting. The Earth would finally succumb to the same fate as its satellite. One hemisphere of Earth would be permanently turned toward the Moon, while the other would be permanently turned away. Imagine living in this world. If you were born on the hemisphere facing the Moon, let's say in the future ruins of the Americas, the Moon would hang motionless in the sky, a fixed monument among the moving stars. It would never rise, and it would never set. It would simply be there, waxing and waning through its phases, a constant companion watching over the landscape. You would grow up, live your entire life, and die, and the Moon would never have moved an inch relative to your horizon. But if you were born on the opposite hemisphere, perhaps in Europe, Africa, or Asia, you would never see the Moon. You could travel the oceans, climb the highest mountains, and gaze up at the clearest skies, but the Moon would be a myth. It would be a legend told by travelers who had journeyed to the moon side of the world. The night sky on the far side of Earth would be empty of the silver lantern that has guided humanity for so long. It would be a darker, lonelier place, populated only by the stars and the wandering planets. This mutual locking is the gravitational resting place for binary systems. We see it happening elsewhere in the universe. Pluto and Charon have already reached this state. They face each other eternally, spinning as a rigid dumbbell in space. The Earth and Moon are striving for this same embrace. They are trying to stop the dance and simply hold each other. However, there is a tragedy written into this future. A cosmic race is taking place, and it is a race that the Earth and Moon may not win. While gravity is patiently working to lock the Earth, the Sun is evolving. Our star is burning through its hydrogen fuel. In roughly 5 billion years, the Sun will exhaust its core and begin to swell. It will transform into a red giant, expanding outward, swallowing the orbits of Mercury and Venus. Its heat will become intense enough to boil the oceans off the Earth and strip away our atmosphere. The timescales are uncomfortably close. The time it takes for the Moon to slow the Earth into a mutual lock is roughly 50 billion years. But the Sun only has 5 billion years left. This means that the Earth and Moon will likely never reach that final, perfect state of mutual stillness. The stage will burn down before the dancers can finish their waltz. The oceans, the primary mechanism for the breaking friction, will likely evaporate long before the Earth stops spinning. Without the oceans to drag against the seabed, the breaking process will stall. The Earth may be left spinning slowly, with the Moon drifting far away when the fiery end of the solar system arrives. There is a melancholy beauty in this realization. The Earth and Moon are reaching for a connection they may never fully achieve. They are striving for an eternal gaze that is forbidden by the lifespan of the star that gives them light. But even if the final lock is never completed, the journey toward it defines our existence. The slowing of the Earth is happening right now, in the silence of your room. With every heartbeat, the Moon is moving a tiny fraction of a hair's width further away. With every breath, the Earth is spinning a tiny fraction of a second slower. We are creatures living on a dynamic stage, caught in the middle of a vast, slow-motion transformation. The stillness of the Moon, then, is not just a curiosity, it is a promise. It is a preview of what the Earth wants to become. The Moon has already finished its evolution. It has reached the quiet endpoint of planetary life. It is waiting for us to catch up. When we look at the Moon tonight, we should not see a dead rock. We should see a mirror. We should see the reflection of our own future. The cratered, silent face, looking down on us, is a reminder that in the cosmos, energy eventually gives way to entropy. Chaos gives way to order, and noise gives way to silence. The reason the Moon doesn't spin, from our perspective, is because it has surrendered to the bond it shares with Earth. It has given up its independence to stay close to us. It is the ultimate act of celestial loyalty. We began this documentary by asking a simple question: why does the Moon look so still? We have traveled through the geometry of orbits, the crushing grip of tidal forces, the fire of a planetary collision, and the cold shadows of the far side. We have seen that the stillness is an illusion created by perfect motion. We have seen that the silence is the result of a violent history. The Moon spins, but it spins for us. It keeps time with our world, beat for beat, step for step. It is the silent sentinel that calms our winds, lengthens our days, and lights our nights. So, as you drift off to sleep tonight, visualize the Moon hanging in the velvet darkness above your roof. Picture the invisible tether of gravity connecting the center of the Earth to the center of the Moon. Feel the gentle, rhythmic stretch of the tides lifting the oceans and the ground beneath you. Understand that you are riding on a world that is slowly winding down, guided by a companion that has already found its peace. The universe is a place of immense forces and terrifying scales. But right here, in our little corner of the solar system, it has arranged itself into a lullaby. The moon watches, the earth spins, and together they drift through the cosmos, bound by a force that is as old as time and as constant as the night. The dance continues, slower and slower, moving toward a final, eternal stillness that waits for us in the dark. Good night.